So we will discuss deadbeat response as this topic today, and what is deadbeat? Deadbeat response. This is very unique for discrete time control systems. You will never see anything like deadbeat response or deadbeat control in continuous time control systems. Because what is the reason behind why it is only existing in deadbeat response is the sampling period T. The sampling period T. Sampling period T and the settling time of the system are directly proportional here in this case, because settling time, if sampling period that is chosen is very high, then you are bound to lose certain information. That is always well and good, but settling time also of the system that is also increasing if the sampling period is very high. And there is one more problem here. If the sampling period is chosen to be very small, then the settling time also becomes very small. It means the response is much faster, but you require very large magnitude of the control signal to be given to the system, otherwise it will not reach the final steady state value. Therefore, the sampling period, choosing the sampling period must be having some trade-off between these two. And if sampling period is, if the magnitude of the control signal, if it is very high, then it might reach a saturation stage where the system might become non-linear. Therefore, we doesn't require those problems here. The problem here is choosing sampling period T in such a way that there is a trade-off between the magnitude of the control signal and the speed of the response. Speed of the response is indicated by the settling time. So this is what is required. Now what is this deadbeat response? Now we have just now indicated that sampling period is very important, and keeping this in mind, we will just go and see the basics behind deadbeat response. Deadbeat response is nothing but bringing all the initial conditions to zero. For example, let us say x of k plus 1 is equal to g into x of k plus h into u of k is our original system. Now we can use the feedback signal u is equal to minus k x of k. Minus k into x of k. Now upon substitution, what do we get? X of k plus 1 is equal to g minus h k x of k. Substituting this here, right, we get this. Now what is the solution of the state equation? Of this equation, x of k is the solution, where g minus h k power k into x of 0 is the solution of the state equation, right. Now in this, to find out this solution, or here the thing is, if all the elements of all the eigenvalues of g minus hk, all the eigenvalues of the matrix g minus hk lie inside the unit circle, if they lie inside the unit circle, right, then it is possible for us to, the system is asymptotically stable. Then the system is asymptotically stable. If all the eigenvalues of g minus hk are lying inside this, and g minus hk are indicated by mu's, right? That is, you can say we have desired eigenvalues as mu1, mu2, mu1, mu so on, right? So this, if all these eigenvalues are chosen to be inside the unit circle, then the system is said to be asymptotically stable. Now to this, for this deadbeat response, what is it? We require all the initial states to be brought down to zero. Initial states of the systems to be brought down to zero, or origin. Right. How is it possible? In this deadbeat response, there are n sampling periods are sufficient to bring the initial states to 0 within the inside the unit circle, right? N sampling periods are sufficient. That is what we will show. N sampling periods are sufficient to bring down the initial states from their initial locations to 0, the final steady state location, right? So this is called asymptotically stable system, right? Now with this we will try to find out what is the order of the system here. With this in mind, now here nilpotent matrix plays a very vital role. Nilpotent matrix plays a vital role here. For example, nilpotent matrix is 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0. This is a nilpotent matrix. Now if I consider a 4 by 4 nilpotent matrix, 4 by 4 nilpotent matrix, which is 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0. Now this is a nilpotent matrix. For this, what is n square? N square can be found to be 0, 0, 1, 0, 0, 0, 0, 1, and the remaining rows are zeros. Similarly, what is n cube? N cube is 0, 0, 0, 1, and the remaining rows are zeros. That is nilpotent matrix. And n power 4, it is a 4 by 4 system. So n power 4 is a 0 matrix. Now if it is possible for us to find out this nilpotent matrix in this system, then deadbeat response is possible. Deadbeat response is possible. Okay. Now this is what we will have to see here. Nilpotent matrix. Just this is an understanding which we will have to keep in mind, and we should bring down those values. Okay. Now this is G minus HK. Okay. Now what is the characteristic equation for this equation? This is Gi minus G plus Hk, which is equal to 0. Now let me consider this to be Z power n plus alpha 1 Z power n minus 1 alpha 2 Z power n minus 3 plus so on, plus alpha n minus 1 Z plus alpha n equal to 0. This is our desired characteristic, or this can be equated to Z minus mu 1, Z minus mu 2, Z minus mu n, which is our desired pole locations. Our desired eigenvalues, desired pole locations are mu 1, mu 2, mu n. Now this deadbeat response appears when you are going for feedback, right? When you are going for feedback and you wanted your system to move to a certain location, desired location with such eigenvalues. Now it is necessary for us to state that if all the eigenvalues are zeros, if all the eigenvalues are zeros, that is mu n equal to 0. If all these eigenvalues, are zeros, are 0, that is mu 1 is equal to mu 2 is equal to mu n, so on, equal to 0. And it means that this alpha 1s also will be going to alpha 1, alpha 2, so on, alpha n is equal to 0. Then when this is 0, all these are zeros, what is happening? This becomes z power n. Right. Z power n is our system. Okay. Now with this in mind, we can just have another picture here, which is a transformation. Let us consider we have a transformation matrix. T is equal to or x of k is equal to t into x cap of k, where T is the transformation matrix. T is the transformation matrix, which is already discussed in our previous class, where T is equal to mw. T is equal to mw. Now if I substitute it here, x of k plus 1 or x cap of k plus 1 is equal to T inverse gt x cap of k plus T inverse h u of k. Okay, so from this equation we can derive this equation using this equation. Okay, now T inverse gt, I'll consider it to be g cap x cap k plus h cap u of k, where g cap is equal to T inverse gt, h cap is equal to T inverse h. Now this is what we are substituting it here. Now we have our u of k is equal to minus k into x of k, where x of k is T x cap of k. Now substituting this here, what is x cap of k plus 1 that we are going to get? G cap minus h cap k T x cap. Right. If I substitute this in this equation, g cap minus h cap kt x cap, h cap kt x cap. Now this is what we are going to see. Right. Now let us discuss what is happening to g cap minus h cap kt. The system that we have considered already here is a completely state controllable system. Since the system is completely state controllable, and if we see that we are going to have the controllable canonical form of the system, then g cap will be is T inverse gt, which is nothing but 0 1 0 0 0 0 1 0 0 0 0 1 minus an minus 1 an minus 2 minus a1, and h cap is equal to T inverse h, which is nothing but 0 0 0 1. This we already know from previous lectures. Many of our lectures we have discussed controllable canonical form to be of this. So g cap, if I put it in that form, 0 1 0 0 0 0 1 0 0 0 0 1 minus an minus 1 an minus 2 minus a1 minus h cap 0 0 0 1 into kt. kt is nothing but minus an minus 1, so on, minus a1. That we already discussed in this just before class, just a few moments back, right? Now what is happening to this system? Just multiply this and get this matrix here. If you multiply this, this is a n by 1 row, and this is 1 by n row. So you are going to get an n by n matrix. N by n matrix, this is 0, 0, 0. The first rows all are zeros, and second rows, all the rows are zeros. Okay, until the penultimate row. And here we are going to get minus an minus 1, minus an minus 2, minus a1. And here we are having this as 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, minus an minus 1, minus an minus 2, so on, minus a1. Now getting this answer, what do we get? 0, 1, the first row is this 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. The first n minus 1 rows are taken from this because the remaining are zeros here, and minus an minus of minus an, the last row becomes zeros completely. Now this is the nilpotent matrix. This is the nilpotent matrix, and the nilpotent matrix we can find out that based on the order of the system and how much is the G cap minus H cap T is equal to nilpotent matrix. Nilpotent matrix. Okay. And what is the solution of that system which we have got? X cap of K is equal to G cap minus H cap KT into X cap of 0 into X of 0. This is power K into X cap of 0, right? So initial state. Now what is the definition of this? This is the solution of the state equation. Solution of the state equation. Solution of the state equation indicates that it is possible for the system to transfer the state of the system from initial state to any desired final state within k sampling instance. K sampling instance. And here the nilpotent matrix here is an n by n matrix. It is an n by n matrix. Now, if it is a fourth order system, then n power 4 is equal to 0 matrix, right? That is, it is taking 4 sampling periods to convert the system to 0. Now this, when will it go to 0? K sampling instance. That is, the order of the system is n here. So n sampling periods are sufficient. N sampling periods are sufficient for the system to bring down the initial states from their location to 0, right? So that is what is deadbeat response, and therefore time period is very, very critical in finding out the deadbeat response, and you should be able to find out the settling time with respect to sampling period, and sampling period must be chosen in such a way that the magnitude of the control signal, scalar control signal, must not be, and the control signal must be unbounded. That is the condition here. It must be unbounded. You can make it to any value. You should be in a position to increase the magnitude of the signal to a certain extent, to a very large extent, and beyond which, if it is going, the saturation comes into picture, because everything is a physical system, and limitations are existing for all the systems, therefore saturation will be existing, and therefore you should have a trade-off between the large magnitude of the control signal, input vector or scalar input signal which is unbounded, and also the settling time. Therefore T must be chosen in such a way that you are having the signal, the deadbeat response much faster.